Today we're going to be breaking down how computers are able to count while only using the digits 0 and 1. Let's start by comparing the decimal number system, which is the number system we use every day, to the binary number system that computers use. A decimal number system uses 10 digits, 0 through 9. However, the binary number system only uses 2 digits, 0 and 1. That leads to the question of how we represent the number 2 in binary. It turns out the answer is pretty straightforward. We use double-digit numbers. Just like how we would write a 1 followed by a 0 to represent the number after 9 in the decimal number system, we use a 1 followed by a 0 to represent the number after 1 in the binary number system. To better understand this, let's take a closer look at how we represent numbers with multiple digits in the decimal number system using the number 3894. In order to dissect what each digit in this number means, I'll write 3 values below it. The first is the place, which is the size of the number that it represents. Next is the power, which is just the place written in exponential form. And finally, there's the value, which is the digit in the number times its place. So, going one at a time, 4 is in the ones place and represents 4. 9 is in the tens place and represents 90. 8 is in the hundreds place and represents 800, and 3 is in the thousands place and represents 3000. So if we add all those numbers back up, we get our original number, which is 3894. Next, let's try this with the binary number 111100110110. So starting with the 0 on the far right, we're going to write the place, power, and value, just like we did before. However, there's going to be one key difference. If you notice in the power column, we're starting with 2 to the power of 0 instead of 10 to the power of 0. That's because in the binary number system, there is no digit for 2. So just like how in the decimal system, there's no digit for 10, so each place represents a power of 10. In the binary system, there's no digit for 2, so each place represents a power of 2. So starting off on the far right, just like in the previous example, 0 is in the ones place, and 1 times 0 is 0, so its value is 0. Next, 1 is in the twos place, so 2 times 1 is 2, so its value is 2. Then the next one is in the fours place, so its value is 4. The next 0 is in the eights place, so its value is going to be 0. And you'll observe this pattern continue, where if the digit is 1, the value is equal to the place, and if the digit is 0, then the value is 0. When we add up all those values at the bottom, that's how we get the final value of this binary number in decimal representation. So, adding up all these values together, you're going to get the number 3894, which is the same value that we were using before. Also, an important thing to note here is in order to distinguish between binary and decimal numbers, we're going to put a subscript 2 next to the binary number and a subscript 10 next to the decimal number in order to differentiate between the two. Another way we can improve our understanding of the binary number system is by counting in the binary number system. So on the left here, we're going to have the numbers 0 through 9 in the decimal format, and on the right, we're going to have the binary equivalents of those values. So starting with 0 and 1, those are just going to be the same as the decimal system. But once we get to 2, we have a 1 in the twos place and a 0 in the ones place. Then 3, you go to 1, 1, and then again for 4, since it's power of 2, it's going to be a 1 followed by 2 zeros. Then 5, which is 101, 6, which is 110, 7, which is 111. Again, we reach another power of 2, this time 8, which is going to be 1 followed by 3 zeros. And finally, we have 9, which is 1001. Next, let's practice converting from a decimal number to a binary number. Let's practice with the number 825. First, we keep writing powers of 2 until we get to one larger than our current number. In this case, we'll stop at 1024, since 1024 is greater than 825. Next, let's construct a table with 3 columns. Binary, which is where we're going to be writing the digits for the binary number we're constructing that will be equal to 825. Value, which we'll use to store intermediate values for our calculations. And then the place row will represent the place that each binary digit will represent. To start, let's write our value 825 in the leftmost value slot. In order to do this conversion, we'll first compare the value with the place. If the place is smaller, we can write a 0 in the binary row, otherwise we'll write a 1. Since 825 is smaller than 1024, we'll write a 0 in the binary row, and then write 825 in the next column over. The reason it makes sense to have a 0 in the 1024's place is that if we had a 1 there, our binary value would have to be greater than 1024, which means it couldn't be equal to 825. Next, let's compare 825 to 512. Since 512 is smaller than 825, we'll write a 1 in the binary row above it, and then for the value next to it, we're going to subtract 512 from 825, which is 313. Again, this makes some intuitive sense to have a 1 in the 512's place, because if there was a 0 there, our binary number would be less than 512, so it couldn't possibly equal 825. The reason we're performing subtraction is because now that we have written a 1, we've accounted for 512 of the value, so we only have 313 unaccounted for. Continuing on, 313 is bigger than 256, so we'll write a 1 and subtract 256 from our value to get 57. 57 is less than 128, and it's less than 64, so we'll write a 0 for those next two places and move the 57 forward. 57 is bigger than 32 though, so we'll write a 1, and then subtract 32 from 57 to get the value 25. 25 is bigger than 16, so we'll write another 1 and subtract 16 to get 9. 9 is bigger than 8, so we'll write a 1, subtract 8, and now we only have 1 left. 1 is bigger than 4 and 2, so we're going to write zeros there. However, it's equal to 1, so we're going to write a 1 as the very last digit. Now that the value minus the place is 0, we know that our conversion is complete and we've successfully converted 825 to binary. Let's next remove the 0 at the beginning of the number, since a 0 at the beginning of any number doesn't provide any useful information, and then write it out. 825 is equal to 1100 111001 in binary. To check our work, let's convert the binary number back to decimal. First, we'll write out all the places in exponential form, where green is for a 1 digit and red is for a 0 digit. Next, we'll evaluate the value of those exponents. Then we'll remove all the red numbers since they correspond to 0 digits. And finally, we'll add up all of the green numbers, and if we did our math correctly, we should get 825. And sure enough we did, so we know that our process worked. Next, let's take a look at what's going on under the hood when we say a computer stores information in binary. The smallest unit of information a computer can store is a bit, either 0 or 1, off or on. When discussing computer data, we typically are talking in terms of bytes, which is 8 bits. You may be familiar with the term byte because it is often used to discuss the amount of storage on a phone or computer, which is typically measured in gigabytes, or GB for short. A gigabyte is equal to 1 billion bytes, so your typical 64 gigabyte phone can store 64 billion bytes. That number is almost too big to comprehend, so let's zoom back in on a single byte and take a closer look at how a computer organizes all of the data that it needs to store. In this table, we're going to be analyzing information density, which is a measure of how many different values can be stored in a fixed number of bits to better understand the importance of bytes. Starting off with just 1 bit, there's only 2 different values that it can have, 0 or 1. Bumping it up to 2 bits, there's now 4 different combinations, 0, 0, 0, 1, 1, 0, and 1, 1. When you go to 3 bits, there are 8 combinations. You'll notice a trend here, where for each time we add a bit, we're doubling the number of combinations. So for 1 bit, it's 2 to the power of 1, 2 bits is 2 to the power of 2, and 3 bits, it's 2 to the power of 3. When we jump up to 1 byte, then, we go to 2 to the power of 8, because 1 byte consists of 8 bits. So you're going to have 256 different possible combinations. Lastly, we'll take a look at 4 bytes, which has over 4 billion possible values. 4 bytes may seem like an arbitrary number at first, but it is actually very important because it is the standard size for an integer or number across all computers. Unlike humans who can just add an arbitrary number of digits to a number, a computer will actually set aside a fixed number of bits for a number it is keeping track of. So instead of just starting off with 1, it will start off with 31 zeros followed by 1 1 to represent the value 1. This has some benefits and some drawbacks. It allows computers to perform computation more efficiently with specialized hardware, but the downside is that if a computer wants to go above that 4.2 billion number limit, a programmer must request more bytes ahead of time. Modern programming languages may do this request behind the scenes, but either way, a number is almost always going to start off by using 4 bytes. And that is it for this video. Thanks for watching, and if you have any questions or comments, feel free to drop them in the comment section below. And stay tuned because next time we are going to be diving even deeper into how computers represent negative numbers.